is the basic result in MRA theory, and I already motivated it a lot in the sense of saying, once we have this theorem, which is for the real line and for dyadic wavelets, going for much more general situations might look technically difficult, more difficult or complicated, but we're giving you the basic idea with this result. But in order to do this, some very interesting things bring to bear. So I'm going to spend the first part of today talking about conjugate mirror filters and unitary matrices. And these types of filters arose in the speech community, and they still are when they're doing coding, compression. And basically, in a very nice mathematical way, I'm going to say that H in L1 of the torus is a conjugate mirror filter if H of gamma plus squared plus H of gamma plus a half squared is equal to 2 almost everywhere. And once again, if you don't know measure theory, you don't have to. You get the almost everywhere. Well, right off the bat, that tells us that note H belongs to L infinity of the torus, and the L infinity norm of H on the torus is less than or equal to the square root of 2. So if you recall, L infinity is contained in L13, which is contained in L12. They're all contained up into L1, right? So, so this H in L1 is sort of a fake hypothesis, but I wanted to start with the most general situation. Okay, so proposition. So some of these things I'm not going to prove just in the interest of time, but I'm not skipping any hard detail. In fact, I will show you the difficult details when I can. So proposition, if H is in A of T, which I will talk about in just a moment, and H of n is equal to the integral, it's the Fourier coefficients. Am I using plus or minus here? Minus, plus 2 pi I and gamma. Then we have the following formula for then H is a conjugate mirror filter if and only if we have the following relationship for the coefficients, namely the sum of over n of H of n minus 2j and then H of n minus 2k conjugate is the Kronecker delta, namely it's equal to 1 if j is equal to k and 0 in this case, in this case, the L2 norm of H, even though, when I talk about this in a minute, I'll explain that this is contained in L infinity, but the L2 norm of H is equal to 1 and the L2 norm of H squared is less than or equal to the square of the L infinity norm, and that's less than or equal to the A norm. And by definition, that's just the sum of H of n in absolute value. So let me just comment on this. This is the space of absolute convergent Fourier series. So just as an aside, A of the torus is the space of absolutely convergent Fourier series. And because of that, and those are continuous functions, so they're contained in the continuous functions of the torus, which of course is contained in L infinity. So if we have a sufficiently regular function, then that guy there is going to be the conjugate mirror filter, if and only if you have this property with the coefficients. Okay. Now, basically, the proof is an exercise, and I won't assign it as an exercise, but all you do is you write out the Fourier series of these two functions, and you're going to, by doing the proper manipulation, you'll get this. Okay? It's a calculation. Okay. Now, I'm going to say some things you know very well from linear algebra, because linear algebra plays a very interesting role in all of this. So, definition, let U be a matrix, the n by n, where U, J, K are complex numbers. And then U is unitary if the conjugate, the Hermitian conjugate of U operating on U is equal to U operating on the Hermitian conjugate is equal to the identity. So we've studied that in linear algebra probably. And in the case of finite matrices, you don't need both of these. If you have this equal to the identity, then you've got this equal to the identity. But in the case of infinite matrices, you actually need it. It's an amusing fact. So just to write everything down, U star, just in case you've forgotten, U star is equal to this matrix here, where U, J, K star is equal to U, K, J, okay? And because U, since U is a matrix, U can be considered a mapping from L2, or doesn't matter, any L2 space on Zn into L2 of Zn. Now, this is absolutely meant to mislead you. One doesn't think of matrices this way. I mean, one doesn't think of these spaces. But I'm just thinking of matrix multiplication and looking at vectors of length n. I'm thinking of those as being on L2, as members of L2 of Zn. So I'm absolutely correct here, but it's being overly fancy, except that I do want to think in terms of operators. Okay, unitary map, the unitary matrices. Question? Oh, you had a question, sorry.
Zn doesn't mean 0 and 0, right?
I'm thinking of the integers mod n. Just what I'm doing is, by looking at L2 of that, I'm just looking, all I'm really looking at here is, this is actually Cn. Right? So we used to have a governor of the state who used to refer to certain people with certain political views that were different than his as a feat, E-F-F-E-T-E. And this is an effete way of saying something that you all learn in linear algebra. Okay. Now, there's another proposition which you know from linear algebra. U equals U, J, K, n by n is unitary if and only if it's column vectors and hence row vectors. Vectors are orthonormal. And that's going to play a role in how we think in terms of, and that's in your standard linear algebra books. Okay, now for our point of view, let H0 and H1 be in L1 of the torus, and define U of gamma to be equal to 1 over the square root of 2 of H0 of gamma, H0 of gamma plus a half, H1 of gamma, H1 of gamma plus a half. Now, I'm just writing these as propositions because, as I say, this actually in linear algebra books, this is also quite easy proposition. U, this U here, is unitary almost everywhere, because after all, this is defined almost everywhere. But once again, if you don't know what it means, don't worry about it. U is unitary almost everywhere, if and only if H0 of gamma squared plus H1 of gamma squared is equal to 2, almost everywhere. Once again, more or less a straightforward calculation. For the couple of you who came in late, as you know, Nate sent you all of the exercises till now. And I was making a big deal about only doing numbers 3, 7, 13, and 42. And everyone, well, not everyone, but I was getting confused because of the changing of numbers. You have 45 problems more or less, hand in 15 on the last day of class, plus your projects. Okay, then the final one of these elementary propositions is the following. U is unitary almost everywhere, if and only if H0 and H1 are conjugate mirror filters. And we have the following relationship. H0 of gamma, H1 of gamma conjugate, plus H0 of gamma plus a half, H1 of gamma plus a half conjugate is equal to 0. Almost everything. And there you go. Okay, now these, we're going to be doing some fairly serious computations today, but I'm not cheating you by not giving you these. These are more or less straightforward calculations. But there's a little bit of shock value because we have a, well, maybe not. You can see the, we're tying together, looking at unitarity in terms of column matrices being orthonormal, and in this way. In fact, you can almost see how the second proposition follows from that, right off the bat. Okay, now something that's not quite as easy as the following. And it's a very fundamental component of the basic MRA theorem. So here's the, I'll even call it a theorem. But this is all material that if you look at some of the classic books on filtering in electrical engineering, like, well, P.D. Fighting-Anathon's book that we've talked about, Beverly and Kovacevic and other books, basically it has nothing to do a priori with labels, but it's, it has to do with coding involved in speech processing and the like. So let H0, H1 be an L1 of the torus, and define U as above. So let's call that star. That is star. Then U is unitary almost everywhere. We already have a criterion, but now we're upping the ante a little bit. If and only if H0 and H1 are CMFs, looks the same as the previous proposition until now, and there exists K, one periodic, such that H1 of gamma is equal to K of gamma, H0 gamma plus a half conjugate almost everywhere. And k of gamma plus a half is equal to, well, I'll just put it plus k of gamma is equal to 0 almost everywhere. And k, the absolute value, is equal to 1. So, what we're doing is, here we've got the H0 and the H1 being involved in the characterization of unitarity. And here we're introducing another function, k. And it turns out that a fundamental component of the basic MRA theorem, which we're going to be proving shortly, is really saying clever things about what k is. And I like the proof of this because sometimes people don't do it. Not because they don't know how to do it, because I guess they would think it's obvious. But I like the fact the way we have to cut up the torus to do it. And this idea of decomposing a base space in an interesting way arises in lots of places. I mean, those of you in harmonic analysis should deal with the Calderon-Zigman decomposition theorem. But even in wavelet theory, when you do wavelet frames and the like, this sort of thing happens. There are other places, perhaps, but one place I know is an article I wrote in Triber in order to characterize wavelet frames. And by the way, for your projects, there are problems in that area that still need to be resolved. If anyone wants to read that paper, or at least the pack concerning this decomposition, be my guest. I never, Triber and I did not finish doing those calculations. For the paper we did, but there were other calculations. Okay, so let's prove this. Let me get over here. So suppose, and I've been a relatively good voice so far with the almost every way, but let me live wildly now and suppress the almost every ways. Okay. Suppose U is unitary. Okay. Then, by that proposition by right, we have that H1 of gamma, H0 of gamma conjugate is equal to minus H1 of gamma plus a half H0 of gamma plus a half. And now by decomposing the base space, what I meant is the following. Let, and this is an elementary case of it, as I say, it can get much more complicated. And there are still things to be done, at least in the frame case. But let A be equal to a set of gammas such that H0 of gamma is equal to 0. And let D equal a set of gammas such that H0 of gamma is not 0. And then if we do that, then of course, then A intersection D is empty. and A union B is equal to the whole torus. So, without loss of generality, assume the measure of A is positive. Okay, then in that case, if gamma is in B, define K of gamma to be equal to so gamma's in B, so that means H0 of gamma is not 0, so I can have it in the denominator, H0 of gamma, and we'll look at its conjugate just to keep things correct. And then up here I'm going to have minus H1 of gamma plus that. And so, if gamma is an A, gamma is in A, then H0 of gamma plus a half is not 0. Why? Well, since H0 is a conjugate mirror filter. Because of this proposition, we're assuming unitarity, so H0 is a conjugate mirror filter, and so since gamma is in A, that means H0 of gamma is 0, so that means this has to be non-zero. And so in that case, therefore, if gamma is in A, let K of gamma be equal to H1 of gamma divided by H0 of gamma plus a half. Well, then we can write down that H, by this one here, then H1 of gamma is equal to K of gamma H0 of gamma plus a half on the torus. Because if gamma's in A, then we have it from this equation, and if gamma's in B, then we have if gamma's in B, then we have this times this. Okay, and then if I look at gamma plus a half, check my notes here. I mean, I did it. So gamma's in A, we're okay. Gamma, we only have to check gamma in B. So gamma in B.
I think you use your relation up above on the left side.
Up above on the left side? Over here?
Yeah.
Oh, right. There you go. Thank you. Okay, Tom. So, we have the whole thing on we've got this relationship here. Okay, so this is what was to be proved, as far as that goes. Also, K of gamma plus a half to minus K of gamma. And I've got to prove that too. That's one of the things about it. And why is that true? Well, let's go over here and complete it. That's true because we've already defined when gamma is in A, K is equal to this guy, and when gamma is in B, K is equal to this guy. So let's just take the convenience gamma in A and consider gamma plus a half. So what is K of gamma plus a half? So we just compute, and we have that K of gamma plus a half is equal to H0 of gamma plus a half conjugate minus H1 of gamma plus a half plus a half. And so this is just equal to minus H1 of gamma over H0 of gamma plus a half. But that's what K is. But K of gamma is actually equal to H1 of gamma divided by H0 of gamma plus. So we're done. Okay. So we have this, I'm going to omit doing this one, it's the same sort of calculation. So basically we have this direction. So, and then for the other direction, conversely, so let's look at this direction here. We want to prove unitarity. Right? And in order to prove unitarity, we are assuming that the H0 and the H1 are CMFs, and we're assuming all this stuff here. And so, thus, the column vectors of U stack have norm 1. Well, for any particular gamma, we're thinking of just the usual Euclidean norm back to by the CMF hypothesis. Further, I just write that out. U star of gamma is 1 over the square root of 2. And then by this formula here, we have this is equal to H0 of gamma. I erased what U is, but basically I just now have H0 of gamma plus a half, because I'm looking at the transpose. And then for the H1 of gamma, well, H1 of gamma, I can write down in terms of my hypothesis here. And so that's K of gamma conjugate H0 of gamma plus a half. And then I'm going to have my H1 of gamma plus a half, but that's then just K of gamma plus a half conjugate H0 of gamma. So I've just written down what the definitions are for U, given my hypotheses over here. This one here, that's all I've used so far. And so in order to prove that U star and hence U are unitary, we must show, so it's sufficient to show, that 0 is equal to, just look at the inner product of these two column vectors. So it's sufficient to show that 0 is equal to, when we look at the vector H0 gamma conjugate, H0 gamma plus half conjugate, inner product with K gamma H0 of gamma plus a half, and the other vector, the point of that vector is K of gamma plus a half conjugate H0 of gamma. Opposed to the sign for the vector and like that. So that's all we have to show. And that turns out to be, I can erase the statement now because I'm done once I prove this. So let me put it close to it. I'll just do it in the top part here. So the right side, right-hand side is equal to, I'm just going to do the dot product. So I get K gamma, and then H0 gamma conjugate, H0 gamma plus a half, plus, by the way, I'm going to conjugate on the K here, and no conjugate. No, that's okay. And then K gamma plus a half conjugate, and then H0 gamma and then H0 gamma plus a half. What did I do wrong here? Yeah.
Are you writing the inner product so that you take the conjugate?
Yes, and that's what I forgot to do. I supposed to take the conjugate in the other side. So when I do that, so there's no, when I multiply that times that, I get the conjugate just becomes nothing here, right? And then H0 is with the conjugate. And then this one here is with a conjugate. And then times that also has a conjugate. And then this one here is K without the conjugate. Sorry. H0 with the conjugate. And that with the conjugates. Every once in a while you have to go to the bar, right? So this is equal to, and now we're done. This is H0 gamma, H0 of gamma plus a half, K of gamma plus K of gamma plus a half. And that's equal to 0 by half one. Okay, I left out a couple of.
Why is that 0? I thought it was great. That's part of the assumption. Okay, okay.
It's not an assumption. Yeah, it was going the other way.
Right.
Okay, except for a couple of details which were, I was not cheating you on, I did the whole course. Now, once you have that result, we can write down, I'll call it a corollary. By the way, there are little questions here which may not be so interesting, but let me just write down one of them and then we'll go to the corollary. So, remark. If you let H0, H1 be an L infinity of the torus, and assume H0 is a CMF, and H1 of gamma is equal to K of gamma, H0 of gamma plus half, where K of gamma plus K of gamma plus a half is 0 and K is one periodic. So, question, is H1 a QMF? Answer, not necessarily. Not necessarily. For example, if I define things this way, what I have is, in fact, just writing out what I have to look for the definition of a conjugate mirror filter. What we have is we've got that H1 of gamma squared, now plus H1 of gamma plus a half squared. And when you write all that stuff out, what you pick up is you get this equal to twice times K of gamma squared. Well, if we had the unimodularity, then it would be a conjugate mirror filter. But note, if K of gamma is equal to sine of 2I gamma, then we have that, but of course we don't have that is equal to 1. So just a little technicality that we need, that unimodularity also. Okay, so now just upping the ante a little bit on the theorem, and we're going to actually be using this form of it. We have the following corollary. So same proof, really. Let H0 be a conjugate mirror filter. And therefore it's an L infinity, right? And let F be an L1 then we have that f of gamma H0 of gamma conjugate is equal to minus, these are all almost everywhere, f of gamma plus a half H0 of gamma plus a half conjugate holds if and only if we can write down f of gamma as kf of gamma H0 of gamma plus a half for some one periodic kf satisfying kf of gamma plus a half is equal to minus kf. Okay, so it's basically the same result. And I'm wondering, should I, maybe I've done enough of these details. I could, I mean, there is some proof that has to be involved here, but it's the same sort of proof, so maybe I'll skip it. Okay? Now, what do the K's look like? Because that's actually important when we prove the multi-resolution analysis theorem. Well, if you have the following situation, so this is just a reminder. If you have the following situation, I'll call it example. So, given H0, H1, as in the theorem we just proved, and assume that their Fourier coefficients are related in the following way. Assume that H1 of n is equal to minus 1 to the n H0 of minus n plus 1. Then we can actually compute that k of gamma is equal to minus e to the minus 2 pi I. And the way one does this, in fact, we just write out, I'm going to be doing a lot more of these types of calculations, so I might not do every detail, but in fact, H1 of gamma plus a half, I write out its Fourier series. Now, we're assuming, there are some technicalities with the Fourier series. H0, let me just say it without going through all the theory, but H0 is a quadrature filter, so in particular that it's an L infinity, the torus. Where are its coefficients? Its Fourier coefficients. Well, those Fourier coefficients are actually, we know they're in L2 because H0 is contained in L2 of the torus. But they're in a special space of L2 called the pseudo measures on the integers. But they're in particular they're in L2 though, coefficients. And so when I write down this Fourier series, I'm talking about an L2 Fourier series. And of course we know by Carlson's great theorem that that we have equality here almost everywhere, but in most of the practical matters we're looking with, we don't need to have a nuclear weapon. We can just know by more basic theory. So this is equal to the sum h1 of k e to the minus 2 pi I k gamma plus a half. I've just written out its Fourier series. This is all almost everywhere. And now, if I write out what h1 is by my hypothesis, this becomes equal to the sum over k of h0 of minus k plus 1 conjugate e to the minus 2 pi I k gamma. Because of the way I've now written, after all, I have e to the minus pi I k. And I look at that 2 over 2. And that's minus 1 to the k. And then if I just keep running that through, that becomes equal to, just by doing calculations that are straightforward, e to the minus 2 pi I gamma h0 of gamma conjugate. And because of what we've already shown, we can therefore conclude, I'm skipping some stuff here, but we then obtain k of gamma is equal to e to the minus 2 pi I. Okay, so that's all I want to say about filters. When I actually give courses related to this material, we have a lot of fun by really constructing a lot of these conjugate mirror filters that are a little bit offbeat. And there's a lot of stuff you can do with them. And one of the things about quadrature mirror filters is that you can essentially have perfect reconstruction in these diagrams where you have analysis filters and synthesis filters and all that sort of stuff. Okay, but we're aiming for wavelets now. So in that, with that quest in mind, let's. So I'm done talking just about filters. But in order to get at wavelets, you have to have one or two more little results where the filters play a real role. So I'll call this a lemma. Let phi be in L2 of R. And if you remember from the definition of an orthonormal from the definition of an MRA, we talked about translates being an orthonormal basis of your span. So assume these guys here, and phi is orthonormal. And what that means, of course, is it's an orthonormal basis with its closed span in L2. Assume ta and phi is orthonormal, and that phi hat of gamma is equal to 1 over the square root of 2. H0 of gamma over 2. Phi hat of gamma over 2 almost everywhere for some H0 in L1 of the torus. Okay, that seems like a strange hypothesis, but it turns out, we're going to see momentarily, that it's a very natural one when you're dealing with MRAs. then H0 is in L infinity of the torus, and H0 is a CMF. So we have some interesting hypotheses to get a CMF here. And dilation plays a role, and I'm going to write out functions in a certain way. So how do you prove this? Well, recall we showed this last time. Recall, I think we will take a break in a couple of minutes. Okay? So I realize I'm just sort of dishing this out in a mechanical way, and I apologize for that. Recall, we proved last time that R and phi is orthonormal if and only if the sum phi hat of gamma plus n quantity squared is equal to 1 almost everywhere. Neat result. Well, substituting this one here into that, 1 and 2, substitute 1 into 2. And so if we do that, this gives, if I look now at phi, I'm going to do this in 2 steps. I'm going to get phi hat of gamma plus n is equal to H0 of gamma over 2 plus n over 2. Then I've got that 1 over the square root of 2. And then I've got phi hat of gamma over 2 plus n over 2. So I've got that, and when I actually substitute it into 2, I get that 1 is equal to, I'm just going to square this in absolute value. So this is equal to 1/2 the sum over all n's of H0 of gamma over 2 plus n over 2 quantity squared, and then phi hat of gamma over 2 plus n over 2 quantity squared. Okay, so what can we do with that that's, well, let me just cross multiply right away. So 2 is equal to that. Well, now we do something that we're somehow forced to do. Question? Let me also this is true for every gamma, so it's also true if I replace that with a lambda, and I replace this with lambda. Okay? So we have 2 equal this for all lambda in the torus. Now, what I want to do in order to make forward progress is I'm going to divide it, separate it into even and odd parts. And so this is equal to the sum over n even plus the sum over n odd. And then if I do that, if I look at the sum when n is even, what am I going to get? The n's are even, I'm going to have them in the form 2m. Huh? Right. You're skipping a step for me. So I'm still going to write it all out though. But you're right, it's just a lambda. So this is equal to, I can take out h0 of lambda squared. And then on the other side, I've got the sum, I'm in for it, over m of phi hat of lambda plus m, quantity squared. And then when I go over the n's odd, I can pull out h0 of, well, n is odd. So I have 2m plus 1, so I get a half there. So I've got h0 of lambda plus a half, quantity squared, the sum over phi hat of lambda plus a half plus m squared over all m's. But hark! This is equal to 1, and this is equal to 1. So we verified that we have a conjugate vertical. So therefore, since the left-hand side is equal to 2, therefore h0 is a conjugate vertical. Okay, so I really used the orthonormality because I needed this condition, and I used this scaling equation in the Fourier domain. And we're going to, this result will definitely play a role in what we do with the waves. Now, let's take 5 minutes.